the remaining topic on that we have to do that has to do with vector spaces directly is the idea. Last time we dealt with the idea of vector spaces and subspaces, which are examples of vector spaces. And so we have a new concept now called spanning sets. And the idea that we can write a vector space as the span of some other set. So now this is suggested by this subset test theorem. So let's just review what we had done last time. So we have the idea of a vector space. And then we have four examples. We had n-dimensional column vectors, which are like, and there's an example, RC3. There's an example there. And then the second one was arrows in e to the n, which is the n-dimensional Euclidean space. Basically, it's the space that that mimics how the real world is with straight lines and stuff like that. And so we have arrows, and there's sort of like the addition, the sort of geometric addition formula, and there's a connection between these two. Sort of make a correspondence between a vector up here and a vector down here. And we'll investigate that connection further in later cases. Then we have, say, p to the n. For example, p2 equals the set of quadratic polynomials. So if you compare these two definitions, you can sort of see that A, B, and C here are playing the role of X, Y, Z here, and that the X here does not play a role like X here. Over here, X is sort of like a component that we can freely vary, but X here is just a placeholder. It's just because what we're making a set of is a set of polynomial functions or a set of polynomial algebraic expressions, and that leads to a different idea than numerical equality of polynomials. So there's a little bit. So this takes a little getting used to. And our fourth example was m to the n cross m, which are the matrices, the n row, m column matrices. For example, we could have, say, m2 cross 2, which would equal and we could put X, Y, Z, W in here. It wouldn't make any difference because so this is the set of 2 by 2 matrices, and we have for this we have the vector. We sort of think of this as sort of V. For example, an example of this would be in this space. V would equal 1, 2, 3, 4. So we're thinking of this as a vector rather than as a matrix. So, and the idea would be then that we would be able to add them and multiply them by numbers in the same way that we take vectors up here and add them and multiply them by numbers. And the same way we add two polynomials together algebraically and collect terms in terms of constant coefficients of x and coefficients of x squared. So from those examples, you can see that there's sort of like some common properties. And those common properties, then we turn around and define a vector space as define a vector space as anything that has these properties. Okay, so all of these examples, they're sort of abstracted from all these examples. And the crucial ones are that if I have V and W as elements of some set here. So this is set membership. So I have two objects in this set V, and so here's the properties that have to hold, right? We have to be able to turn around as a commutative property, just the order shouldn't matter. And the same way, if we have three of them, UWU, say, has to equal V plus W plus U. So you could put U up here too, would have to. So if I have any few vectors, then this is the commutative property, this is the associative property, and we have to also have, there's some properties involving numbers. For example, a number where if R and S are real numbers, right? Then R times V plus W has to equal RV plus RW, and R plus S V has to equal RV plus S V. So these are sort of like distributive properties, right? And then with this, we also have an associate, but then we go back and we have an associative property, RSV equals RSV. So neither with the addition or with multiplication do you need parentheses. Okay, and then for every vector V, we say this, for every, well, we need this first of all. I think there is a vector Z such that for any vector V, Z plus V. Oh, no, we're not going to call it Z. We're going to call it the zero vector. The one you just used an arrow. So this indicates a vector. Then we have 0 V has to equal V. And since it's commutative, you have 0 plus V or V plus 0 equals V. So that's an identity element, an additive identity element. And then there's sort of similar to this is we need to require that 1 times V equals V. Sort of a notational thing. We don't really have anything that tells us how to get rid of that's not a 1, that's a number 1. What am I doing? Okay, so it's the number 1. So real number 1 times a vector has to equal just that vector. This allows us to sort of connect up any vector with a multiple of that vector. So it's sort of a notational convenience. So this is sort of like a multiplicative identity element, but it's not a vector. It's related to the number, whereas this is related to a special vector. This has to be something. This is a property that's already existing. And then, so I think, I'm not sure if I've left out any of the properties that, let's see, there's supposed to be 10 of them, but 1, 2, 3, 4, 5, 6, 7. So I must have left some out. So let's look back and see. There's a page when they're back here that are all collected together, just so we can have them in. I have a separate sheet, but I haven't put it up yet that has them all in on one page. Okay, here we are. So, I think what I left off was sort of property 0. V plus W has to be an L. You have to be able to add elements and be a member, and then also R times V has to be a member of it. So essentially these things say if two vectors are members of these two properties, say if like any linear combination is going to be a member of V. So that's where this is sort of a crucial thing, because it sort of says if any linear combination of vectors in V is also in V, you can sort of see, because if A V plus B W, well, we can see that if V is a member of V, then the multiple A times V and B times W are members of V, and this property says they're sum, so we know right away that when you, and this property, even though it seems trivial or it seems like sort of obvious, it is what gives the whole idea of vector space and connects it up with linear systems. Okay, so I think that was like the closure. We've done that, we did that, we have a 0 vector, we did the additive identity? Oh, no, we didn't. Okay, so that's the other maybe crucial one. I don't know, I don't want a page before. I want a page after. Okay, so we had 1, 2, 3, 4, 5. We have 0, and then we have 6 here, which is for every vector V, there is an opposite vector such that opposite vector W such that at least one of these, such that V plus 0 equals the 0 vector. Now, the point is that you can show W is unique. That is, if there's two vectors that have this property, then they would be the same vector. There's only one such. For any given V, there's only one vector W that does this.
So what this is essentially saying is that for every vector V, it has an inverse, which is W, and then when you add those two together, you get 0.
Yeah, I've used the word oppa. So you could say it has an additive. The standard name is additive inverse, right?
Yeah.
But then so it's sort of, and so it has one of these, and it's sort of like an additive opposite, or there's something that cancels it out. That it's this property that's so there, because it's unique. We can say W is equal to minus V. We can give it a name. Okay, and then you can show that minus V or dash V equals minus 1 times V. Okay, so you can show that the other things. So this sort of means that you take any vector and multiply it by minus 1, and that's going to give you the additive inverse or the opposite vector here. Okay, so those are the properties that any vector space, to be a vector space, it has to have. So these are sort of the external properties. Sort of like if you were to ask, well, what's a tiger? You go to a zoo and you can give the external properties. Well, it's something that looks a certain way, it behaves a certain way, but then you could also look at it and ask, well, what's the essence of how did it get to be that way? Is sort of the internal physiology and genetic code that would tell you internally what a tiger was versus some other cat. Okay, so this is the external behavior. This is sort of an external characterization of a vector space. And so we want to go on and find sort of a way to sort of see what it looks like inside. You know, it's sort of internally. And that is this the topic for today. So this has sort of been a review and introduction to sort of looked at sort of the examples of the definition, and then we need to look at subspaces. And so where we had subspaces as an example. And so a subspace, the key idea is a subspace is just another, okay. So let's see. A subspace is a subset of a vector space that is also a vector space. Okay. And so the idea then is that we saw that, well, we could just take a subspace and verify that some subspace had all the properties of vector space. For example, the primary example of this is the solution set of a linear system is a vector space of a homogeneous linear system is a vector space, and any vector space is a solution set of some linear system. So we really haven't changed topics here. We're just sort of making it more abstract. We're just sort of looking at it from a different perspective. Okay, now the thing is that we could verify all those properties to say it's a vector space, but there's a theorem. There's the sort of the crucial theorem, which is the space test theorem, which says two things are equivalent. You have A, V is a, S, subset, that's the subset symbol of V, is a subspace. Well, it's already a subset, so this is just the claim it's a vector space. This is the concept, right? But the test, the practical test of it is that any linear combination of elements of S is in V. So all I have to check, if I want to know, is S a vector space? I say, well, give me, if any two vectors are in S and any two numbers are real numbers, then so if you're given this, then RV plus SW is a member of S. If you can show that this is true, then let's see, if those things and this, then S is a subspace. Okay, so if you want to show something's a subspace, you just take a linear combination and show this. Now, since we want to apply this, since we want to think of, so let's look at an example of this to sort of see how it works. And there's some examples on Rig X. Let's take, say, a set S that equals all the, say, let's just do a two-dimensional example, see how that works. X and Y such that x plus 2y equals 0. Now you recognize this as a linear homogeneous equation in one variable where it's already in echelon form and x is leading and y is free. And so the question is then, if we want to show that this is a subspace, and we could do it with that subspace theorem by saying, okay, I need two vectors, v1, or let's call them v and w. I need two vectors. Well, so that could be like x1, y1, and w equals x2, y2. So these are just I've just chosen these are arbitrary numbers, right? Because v and w can be any vectors. So x1, y1, x2, y2 have to be arbitrary numbers, right? And then I choose any two numbers, any numbers R and S member of R. And I have to show, now, if V is a member of S and W is a member of S, need to show that RV plus SW is in S. Now you can see that S here is a subset of R2. So we're showing essentially that this subset, the set of X and Y such this is true, which is a subset of R2 because it's two-dimensional vectors. If we show this, we know it's a subspace and it has all those 10 properties, even though we haven't verified them directly. That's what the theorem buys us. We don't have to check 10 properties. We just have to check one. Okay, so that's an advantage. Okay, well, let's see how that works. Well, let's form this thing here. R times V plus S times W equals R times X1, Y1 plus S times X2, W2. And then what I'm going to do is I'm going to put this into sort of do the vector operator, multiply the R and multiply the S and add the two vectors. And if you do that, what you get is RX1 plus SX2 and RY1 plus S. I got somehow a W in there, Y2. Do you see? So I multiplied the RRSS, then I added, RX1 plus SX2, RY1 plus SY2. Okay. Now, the question is, I need to show that this is in S. Well, S has a defining property right here. So what if V is in S, then I know something. I know that X1 plus 2Y1 equals 0. And also that X2 plus 2Y2 equals 0 because W also has to be in there. Now I need to, what do I need to show? I need to show that for this vector, right, that R times X1 plus S times X2, that's the X of the combined, plus 2 times the Y component, Y1 plus S, Y2 equals 0. I have to show. I know this. I have to show that this is true. If this is true, this vector will be in the subset. Okay. Well, so what I do is I just multiply this out. Anyway, do you see what I'm doing here, you guys? Okay. So then I have to multiply this out just using ordinary commutativity, and just I'm going to move the ones over to the left and the twos over here. So what I'll get is RX1 plus 2RY1 plus SX2 plus 2SY2 equals 0. Well, I have to show that. So I haven't shown that. The question is this true? Right? So right now, I'm just considering this side here and saying this side equals this. And now here there's an R and R. I can factor the R out. X1 plus 2y1 plus S times X2 plus 2y2. And so these two are equal. And I can keep going down and saying, well, because the first vector is in S, I know this is equal to R times 0 plus S times, and since X2 plus 2y2 is 0 times 0, and that equals 0. So therefore, I verified that this is a subspace, because I verified that any linear combination of vectors in this space is also in the space. It's a little bit complicated because it's not complicated, but it's not something you're used to looking at or thinking about because there's no numbers here. They're all like X's with indices and R's and S's. So it seems you can sort of like, you have to sort of keep in mind that the X's and Y's are variables and the R's and S's are constants. And if you keep that intuition, then you can sort of see what's going on and see the strategy. Okay,